So let's see, we were talking about first variation, and just remind you how that worked. So we've got a submanifold M of dimension M, some higher dimensional Euclidean space Rn plus k, and we were thinking about taking variations of that. So we had a family, what we called phi tx. That's a map from minus epsilon cross m into Rn plus k, same space, and it should have the properties that phi 0x, and we also use, so this should be phi c1, and we also use the notation that phi t of x is just phi tx. The point there is that when you write it this way, you're thinking of t being fixed and this being a mapping just in the x variable. And we require that phi 0x should be identically equal to x for every x, and also that phi tx should be equal to x outside a compact set. So this is for every x in m minus k. So there should exist a compact k. Compact k such that that's true. So you get this picture if you schematically represent m just as a one-dimensional thing, then phi t takes m and gives you a perturbation like that. And it holds everything outside k fixed. So k is set here somewhere. So everything gets fixed outside here, but phi t moves, gives you a one-parameter family. And the main computation was we took the first variation of the volume, d dt, at t equal to 0 of the volume, phi t m intersect k. And we got a nice formula for that. In fact, we found it was simply equal to the integral over m intersect k of the tangential divergence of the initial velocity vector integrated with respect to n-dimensional Hausdorff measure. So here x is the initial velocity. It's partial with respect to t of phi tx, so x at x is partial with respect to t, evaluated at t equal to 0. There we go. So that's what we derived last time, and we made the point that there's an important special case if M is C2 manifold. In this discussion, M only had to be a C1 manifold. But in the special case when M is C2 and X is a tangent vector field, so in other words, X at X is actually in the tangent space. Notice in this setting, there's no requirement like that. X is simply a vector-valued function. X has got components x1 up to xn plus k. So X is a mapping from a C1 mapping from, I should have, this is wrong, isn't it? This is supposed to be C2 because I want the partial derivative to be C1. So X is a C1 mapping from M into Rn plus k. And this is C1 because the phi is C2 and we're taking a first partial here to get the initial velocity vector. All right, so now the special case when M is C2 and X is actually a tangent vector field. Vector field on M. Then we found that you can cook up a phi t. I didn't do this, but I pointed out that you can see the argument for this in the text. It's just an ODE argument, a standard fact, that you can then cook up. There exists a phi t, as in this, satisfying all these things. Let's call it star. There exists a family phi t as in star with phi t m intersect k invariant. So phi t fixes m intersect k. Notice, of course, it moves points in here, but as the whole set, as a set, remains fixed. It doesn't move any. It moves points, but it always moves points back inside the set itself. So this implies that ddt, of course, hn m phi t m intersect k equals 0, of course, so that t equal to 0, any other t for that matter, and so that's 0, and that means that this guy is 0. This is the same thing, so that is integral over m div mx equals 0 if x is a tangent vector field with compact support, of course. Notice that's always assumed in any of these cases. You've got to have x, that is, x identically 0 on M minus a compact set K. So, of course, you need that, but otherwise no restriction except that x is a tangent vector field. Then you get that this is 0. So that's the classical divergence theorem for submanifolds, for C2 submanifolds. It's called the divergence theorem. Okay, and now let's go back to the general case. Go back to the general case when we're just assuming this. X is no longer necessarily a tangent vector field, except that let's keep assuming for the moment let's keep assuming for the moment that M is C2. So we're still assuming that M is C2, but we're certainly not assuming this condition. We're just taking a general one parameter family with general family of perturbations, general family of variations. So X is any map into Rn plus K, so it's completely general. And then, you can always project at any point X, you can always project onto the tangent space. And you can always break X up into its tangential and its normal parts. So we can do that. We can take the orthogonal projection onto the tangent space plus the orthogonal projection onto the normal space. And remember, this is still C1 because we showed that you can take, in the case of a C2 manifold, one of the things we discussed using local coordinate representations, that you can find locally defined orthonormal bases for the tangent space and the normal space. So this is actually a C1 operation, this business of taking the orthogonal projection onto the tangent space and the orthogonal projection onto the normal space. That's a C1 operation. So these guys are still C1 vector fields. And then you can take the divergence of Mx. Well, let's do the integral. Let's take the whole thing. So this first variation, integral over M intersect K, div Mx dhn, is equal to the integral of the divergence of this tangential part. But notice this tangential part satisfies this. It's tangent by definition. So this first part is 0, div sub M of the this is a bit cumbersome, isn't it? Let's just call this guy xt and call this bit x per. That's probably a better notation. So div sub m of xt dhn, that's 0 by this result up here. And the remaining bit is div sub m of x perp, dhn. So let's see if we can work out div sub m of h perp. Well, we know that, remember, as we discussed, there exists, at least locally, there exists C1 vector fields, nu1 up to nu k, which are an orthonormal basis. So with nu1 at x, nu k at x, orthonormal basis for the normal space. Remember, we talked about that when we were discussing second fundamental form. And that means we can explicitly work out x perp. X perp at x is just the sum alpha equals 1 up to k of nu alpha dotted with x times nu alpha, all evaluated at x. Alpha. So div m x perp, div sub m x perp is, now let's see, this is sum I equals 1 up to n of tor I dotted with the directional derivative of this guy. Alpha equals 1 up to k nu alpha dotted with x times nu alpha. Now, let's see. When I've got to use the product rule for differentiation, so I've got to differentiate this bit times nu alpha, but notice that bit gives 0 because nu alpha dotted with tor I is 0 because tor I is tangent and nu alpha is normal. So we actually only get one term out of this. It's when the d tor I hits this guy, nu alpha. So this equals sum I equals 1 up to n tor I dotted with, let's do the sum out here. Let's pull the sum out. Alpha equals 1 up to k. And then it's nu alpha dotted with x times d tor I dotted with d tor I nu alpha. So the other term gives 0. So that's what you get. Now, notice that this is exactly what we defined to be the second fundamental form. So this is exactly minus the second fundamental form of n evaluated at tor I, tor I. That was our definition of second fundamental form, and we're summing from I equals 1 up to n. So that's sort of an interesting quantity. It's not the full trace of the second fundamental form of n, because remember, this is, second fundamental form of m, sorry. This is the full trace. This is the second fundamental form. So this is actually what we called the mean curvature vector. Oh, I forgot we're dotting with x, so it's that dotted with x. So this is what we called the mean curvature vector with a minus sign. We've got that minus dotted with x. So let's summarize then. So what did we get? This we've shown is, so that's just the integral of this. So finally we get integral m intersect k, and there's no need to write m intersect k because in any case x vanishes outside k, so there's no need to do that intersection. You can think of it as an integration over all of m, no problem. So this becomes div mx, the first variation is equal to minus integral over m of h dotted with x dhn. So that's what the first variation looks like. It actually turns out there's two ways of writing. You can either write it this way or you can write it this way. They're equal. So that formula will be very important for us, and we'll come back to that later. So that's as much as we need to say for the moment about the first variation. Okay, now you remember we proved the area formula, and we also proved an inequality about slicing. Remember, if we had a mapping from, we were in a sigma compact metric space, and we had a Lipschitz map mapping into Rm, Lipschitz, and we had a subset A contained in X with HM plus K. This had to be HM plus K measurable. HM plus K measurable, and HM plus K measure finite. Then we got this nice inequality on the slices that you get by using the map and taking pre-images. We got that the integral over Rm of the k-dimensional Hausdorff measure of the pre-image set of points back in the space. Oh, this is A intersect minus 1y. So this slices intersected with A, integrated, the k-dimensional Hausdorff measure, integrated with respect to m-dimensional Hausdorff measure. That was less than or equal to a certain constant. In fact, it was omega k, omega m over omega m plus k times the m plus k dimensional Hausdorff measure of A. Very nice. Oh, times the Lipschitz constant to the mth power. Lip f to the m times hm plus k of A. So that was a very nice inequality, very useful inequality. In fact, remember, it's valid for every k positive. You don't need k to be an integer in that inequality. It's quite useful inequality. And it enables you to get bounds on the slices. You think of these inverse images as slicing by the function f. You take the pre-image of a point y, that gives you various slices, disjoint slices of the original space, and this gives you a bound on the integral of the k-dimensional Hausdorff measure of those slices. Nice fact. Now, there's something called the co-area formula that instead of getting an inequality for this quantity, you actually get an equality. You get an exact formula. That's so the co-area formula. Co-area formula. Co-area formula refers to the case when X is Rn. X is an, or rather more generally, X is an n-dimensional manifold. So C1 submanifold. Contained in some other higher dimension of Euclidean space. Let's say Rn plus L. We normally write Rn plus K there, but I can't do that at the moment because we're going to use this K, where K is reserved for this index here, this dimension. So let's call it Rn plus L, this Euclidean space. So we're sitting in the, so it's the usual picture, M is here. And F is goes from M into Rm, same as it over there, Lipschitz. Then, as I said, the co-area formula is going to give us a bound on this same quantity. So it's going to be integral over Rm hk A intersect f to the minus 1y dlm y is equal to something that looks just like the formula that we had for the area formula, namely the integral over A of J sub mf dHn, and this is valid for every Hn measurable A contained in M. And now I've got to say what JF, where JMF at X is just equal to the square root of the determinant of dF at X, that's the induced linear map of F at X, composite with the adjoint of that induced linear map, dFX, adjoint. Now notice that dFX goes from the tangent space into Rm, and this is all sitting in Rn plus L. So notice that you've got to stare at that a bit to see that it's not the same thing as we had in the area formula, right? The area formula, we had dF star composite dfx, right? It's the other way around now. So let's examine this a bit more closely. So dfx is the induced linear map. So dfx goes from the tangent space of M into Rm. That's linear. It's the induced linear map. And in fact, dfx, remember the definition, dfx hitting a vector v is simply the directional derivative of f in the direction v. And remember, we proved that that makes sense almost everywhere and does indeed give you a linear function of v. That was one of the things we checked about functions on a smooth manifold. So that all makes sense. And you can rewrite this as the sum. Remember, this is linear in V, so we can rewrite it in terms of an orthonormal basis. This is for any V in the tangent space at X. This is supposed to be a mapping on the tangent space. So these V's are in the tangent space. So I can always write any such V in terms of an orthonormal basis. So let's do that. So we get sum J equals 1 up to n Vj tor j, and that means we can pull out, remember this is linear in the V, so I can pull the sum outside I can take the sum outside and I just get the directional derivative in the direction of tor j at x, and here tor 1 up to tor n is an orthonormal basis for the tangent space. Orthonormal basis for the tangent space. So that's what that is. So you see that tells us what the matrix looks like. And remember, F, of course, is just got mapping into Rm. So that's just got its ordinary M coordinates. F1 up to Fm, where each Fj is a real valued Lipschitz function. So this gives us the matrix. So in terms of the matrix, so matrix of dfx with respect to this, with respect to this choice, tor 1 up to tor n for the tangent space, and the usual basis for this is the standard basis for Rm. So this is the basis for Rm, and this is the basis for the tangent space at X. That matrix is simply this guy, d tor j fi. That's exactly what it is, d tor j fi. So now we can work out this. Remember, composition of linear maps corresponds to matrix multiplication, right? So we've just got to multiply the matrices together. So we can get an alternative description of this Jacobian, namely a JFM at x is equal to x is equal to well, here it is. It's just we've got to multiply these matrices together. So that's equal to the square root of the determinant of the sum from q equals 1 up to n of d tor q fi times d tor q fj. Now notice that we're summing on q, so that an ij goes from 1 to m, remember, so f has got components f1 up to fm. So this is an m by m matrix. M by m matrix. So that's what this looks like. So notice it's different, quite different than the quantity that appeared in the area formula. The quantity that appeared in the area formula would, of course, if we use that, that would be 0, because the rank here is m. The maximum rank possible here, remember, f is mapping, here it is here, f is mapping an n-dimensional manifold into Rm, where m is less than n. Oh, I forgot to say that, didn't I? Otherwise, this becomes quite trivial. So here m is less than n. Notice that's the reverse inequality. In the area case, we needed m bigger than or equal to n. So this is the other inequality. This is the reverse inequality, m less than n. So, for this one you don't need any of that, but for this one you certainly need m less than n. So, m less than n. This one's general. There's no assumption on m and n there. There's arbitrary m and k. But for this one we need m less than n. And then the maximum rank here, mapping an n-dimensional manifold into Rm, the maximum rank is m. Otherwise j will be 0. Okay, so that's so we get this identity, and we have a nice formula for the Jacobian. Let's just do one case, special case. An important special case is the case when m is equal to 1. Now in that case, there's only one component here. It's real valued. F is real valued. So this is no longer a determinant. It's just the sum of the partial derivatives of f squared. So in that case, jfmx is just equal to the square root of the sum q equals 1 up to n of d tor q f squared. But of course, that's just the length of the gradient. It's just the length of the tangential gradient of f, first power. So in this case, the co-area formula says integral over Rm of the k-dimensional Hausdorff measure of the slices, set k, dlm y, is equal to the integral over m of grad m, integral over a rather, of grad length of the gradient integrated with respect to n-dimensional Hausdorff measure. So that's a nice thing, and that enables you, of course, to say that a lot of the slices that appear here have k-dimensional measure that's bounded. Maybe some of these could be plus infinity, but the integral is finite because it's equal to this, so almost all of the slices must have finite k-dimensional Hausdorff measure. for example, as long as this integral is finite, which of course would be the case if, for example, if A is compact, then of course this is finite, because this, remember, grad mf is less than or equal to the Lipschitz constant of f, because this is defined in terms of directional derivatives, and each of the directional derivatives has absolute value less than the Lipschitz constant by definition. So this will certainly be finite if A has got finite measure even. This will be finite. In fact, this side is less than or equal to lip f times the n-dimensional Hausdorff measure of A. So that's certainly finite if the n-dimensional Hausdorff measure of A is finite. And that gives you a nice bound on a lot of these k-dimensional, not all of them because this is an integral, but it gives you bounds on a lot of the k-dimensional slices of that you get by using f. Okay, so that's the co-area formula. Now there's a couple of remarks to make about it. I'm afraid I don't have time to give the proof of this, but let me make a remark that'll give you a hint about how the proof should go. Let's take a special case, very special case. One important special case is the case when L equals 0. That means that our submanifold here, remember this is sitting in Rn plus L, and M is n-dimensional. Well, that just, if L is equal to 0, that means M is simply an open subset of Rn, right? So if L is equal to 0, that is, M is open in Rn, an open subset of Rn. That's sort of the trivial case. It's no longer technically a submanifold, it's just an open set in Rn. And and let's take F, very special choice of F. Let's just take F, the projection onto Rm, projection onto the first n coordinates. M coordinates. So in other words, P of x1 up to xn, remember n's bigger than n, so there's more than m coordinates here, just gives you the first m of those coordinates. So that's a very special case of this thing. And let's compute jf in this case. So j sub p at x. What is that? Well, just follow the prescription there. It's the square root of det dq. Tor q's are just the standard basis vector in this case, right? We're in Rn. We're just in an open set in Rn. So instead of tor1 up to tor q, we've got e1 up to eq. So this is the sum q equals 1 up to n dq ith component of p times dq jth component of p. And that's a trivial computation because we're just differentiating coordinates with respect to other coordinates. So in fact, you'll see that this is just the m by n identity matrix. It's just the square root of the m by determinant of the m by m identity matrix, which of course is 1. So in this case, Jp is equal to 1, and the formula, the co-area formula, says, see, what does it say? So you've got to take the k-dimensional Hausdorff measure of the inverse image of P, this projection P. So that's integral HK of P to A intersect P to the minus 1y dLm, this is integral over Rm, dLmy, is equal to just the n-dimensional Hausdorff measure of A. Well, it's Hn of A. So that's what it says. Remember, that's because J is equal to 1 in this case. And remember, we're in Rn here, so that's the same as the Lebesgue measure of A. Now, stare at this for a minute. P is the projection onto the first m coordinate. So in other words, this is exactly the same as the k-dimensional Lebesgue measure of the set of Z, such that the set of Z in Rk, such that YZ is in A. That's what that is. So do you recognize this formula? It's Fubini's theorem, right? So in this special case, it's just Fubini's theorem. So that's what the co-area formula should be. You should think of the co-area formula in that way. The co-area formula is a generalization of Fubini's theorem to a nonlinear setting, where sort of a curvilinear version of Fubini's theorem, where instead of slicing by projections, you're slicing by a general function, general Lipschitz function, and you're integrating those slices. So it's unfortunately, as I said, I don't have time to prove the co-area formula, but I think you can see because of this hint, obviously the proof is going to involve using Fubini's theorem in some way. So the proof of co-area uses Fubini. It also uses the area formula in a clever way. It uses the area formula. Of course, you can't use the area formula on F because we're in a different setting here. We're in the setting where we're mapping an n-dimensional thing into an m-dimensional thing where m is less than n. So you can't directly use the area formula, of course. But you use the area formula on a map that you cook up, a map which has its first m components equal to f, and you tack on some extra components. So you use the area formula, and you also use this general inequality, this one here. Let's call this star. So uses those things, area formula plus star. And by the way, notice that star takes care of the co-area formula in case A has measure 0. Star proves co-area with both sides equal to 0. With both sides equal to 0 in the special case when HNA is equal to 0. Because you see, remember, in this setting where we have m plus k is equal to n, this was general where m and k were arbitrary, but in this setting, n is equal to m plus k. And so this would be Hn of A, so that this side would be 0 by assumption. And then, of course, by the inequality, this is 0. But that's exactly this left side of the co-area formula. So that takes care of the proof of the co-area formula in case the measure is 0. That's an important case that you have to handle in the proof. So that's how you use star. And the rest of the proof uses Fubini area formula, plus this general fact about sets of measure 0 when you've already got the thing in case of measure 0. So I won't say any more about the proof other than that. So take a look in the text. You'll see that the proof is just a couple of pages, and it's rather reminiscent of the proof of the area formula. You break things up into small bits and use the definition of and in particular you use the you use, at a certain crucial point, you use the classical Fubini theorem. But I won't go into details with that. Okay, so that's the co-area formula. Now, there's one very important consequence of that, this so-called C1 Sard theorem, which I want to talk about, because unfortunately it's usually rather neglected. So let me say something about that. So I first have to remind you of the implicit function theorem. Very important theorem, implicit function theorem, one of the basic tools of real analysis, sometimes abbreviated IFT, implicit function theorem. And that goes like this. You suppose that you've got an M, sure I get the notation here. So we're in Rn, and we've got a mapping F going from Rn into Rm, and here we have coordinates x in Rn, and we're going to split them up into their first k coordinates, which we call xi, and the last n minus k coordinates, the last m coordinates, which we call z. So the xi is in Rk, so this is in Rk cross Rm. So k here is equal to, in other words, k is equal to n minus m. M is less than n, same as it is in the co-area formula, right? So k is equal to n minus m. So we're mapping that way. So that schematically we'd have xi. Keep in mind, though, that this is really an Rk space and this is an Rm space, and we've got a mapping F going over here to Rm. For instance, if m is equal to 1, it would be just mapping onto the real line. That would be one case that's important. And you go to any point, so you want to look at the pre-image. So you, the implicit function theorem tells you that you want to solve the, so you take a given y over in this space. Take a given point y, any given point over here in this space. If we're on the real line, it would be a point on the real line there. And you look at this set of points that map to that. In other words, you're looking at the pre-image. So you want to solve fx equals y. So y is given here. That's important to get that clear to begin with. Y is going to be fixed in this discussion for a couple of minutes. And we're trying to solve this. We're trying to find all the solutions x such that fx equals y. That is, really, it's just we're looking to find f to the minus 1y. But see, that's really a system of, notice there are m equations here because we're mapping into Rm. Got m components. So there, and y is likewise y1 up to ym. So this is m equations in n under x is in Rn. N is equal to k plus m. So this is n equations with n, so there are more unknowns than there are equations, and you want to know how to solve that. Well, the implicit function theorem helps you, at least theoretically, it tells you what the solution typically will look like anyway. It doesn't actually tell you how to actually solve it, but it tells you what the solution will look like. Namely, if you start off with the point x0 here, suppose that you've got one solution, x0, which maps to y. So take any x0 in Rn with fx0 equals y, and assume that the partial derivatives with respect to the xi variables, that's these first variables, the first k variables, d xi j, df d xi j, so dfi d xi j. Sorry, that's we want to look at the df dz dzj. Now notice that that's these partial derivatives at x0. These partial derivatives it's an m by n matrix, m by m, so we can take the determinant det equals not equal to 0. So you assume that that's not equal to 0, right? So in other words, the map has rank m, and in particular you get this minor of the Jacobian matrix has non-zero determinant. So that's the assumption. Then you can actually find a small ball. Let me give myself a bit of space here. So suppose the point x0 is up here with coordinates xi0 and z0. Then find a small ball around here. I'll draw it a bit larger just to give ourselves a bit of room, but typically it would be quite small, such that inside the, so let's look at the pre-image. We think of the pre-image maybe as something like this. It could be pretty bad. It could look pretty terrible. So this is f to the minus 1y. The claim is that near the point x0 in a sufficiently small ball, actually that pre-image is just a graph over an open set, let's call it V. So the implicit function theorem says that if this is CQ, where Q is bigger than or equal to 1, and then the implicit function theorem says that there exists rho bigger than 0 and an open V contained in R K, and a CQ map, CQ function U going from V into RK. So U has got K components. It's a vector valued function with components U1 up to UK, CQ function, such that the pre-image intersect with the ball of radius rho, the open ball with radius rho centered at x0, is equal to the graph of U. Very nice theorem. It says that as long as you've got a non-zero Jacobian with respect to m of the coordinates, notice actually there's nothing so special about the last m coordinates. You could equally well do this with respect to any selection of m coordinates. So this really works for any rank m mapping. It's just that it's more convenient notationally to assume that it's the last m coordinates that give you the non-zero determinant. But then you get this result, that the f to the minus 1y is exactly equal to the graph of a CQ function. And you can repeat that. So here's the upshot of that. Notice that this is in terms of our notation from last lecture when we were talking about submanifolds of Euclidean space. This says that the pre-image near the point x0 is a k-dimensional CQ submanifold, right? Because it's the graph of a CQ function. So the upshot of that is if you let C, that is, if C equals the set of X such that the rank of dfx is less than M, so that's the so-called critical set where you don't have rank, so you can't do this anymore. Well, first of all, this is rank, so in other words, but remember that's, for us, that's the same, exactly the same as saying that this Jacobian quantity that we defined here, that quantity is equal to 0. It's clearly the same thing, right? This is 0 if and only if the matrix has got rank less than M. So that's exactly the same. So, and this is a closed set. So C is always a closed set. Remember, F is a CQ function, so it's at least C1. That means these derivatives are all continuous in X. So this is a closed set of points where a continuous function vanishes. So that's a closed set, and that means so C is that. And then, on the other hand, at all the other points, you can do this. Of course, you may have to relabel the coordinates because it's not always going to be the last M coordinates that make things work out, but that's fine. You still get a local coordinate representation modulo relabeling the coordinates, right? So what's left, in other words, is that f to the minus 1y minus c is either empty, which it could be. There may be no x0 to get you started here. We had to assume that there was an x0 to get started, right? There may be no such. It may be empty. But it's either empty or is a CQ, k-dimensional CQ submanifold. K-dimensional CQ submanifold of Rn. So that's very nice, and but there's one extra thing that we can say now, and that is we can examine this. See the co-area formula. At least in this special case, when we're in Rn. So we're just using the co-area formula in the case L equals 0 now. So M is open in Rn. Then, according to the co-area formula, the Hausdorff measure, or integral, f to the minus 1y, intersect A. Now, in this case, let's apply the co-area formula to this critical set, C. It's the set of points where the rank is less than n. So let's apply it to that. So dlmy, integral over Rm. That's equal to the integral of the Jacobian over C, dHn. But of course that's 0 because the JF is 0 in the critical set. So that means that Hn, oh sorry, this is Hk. Hk of f to the minus 1y intersects C equals 0 for Lm rather, almost every y. So this closed set C that we're worried about, which causes us not to get a submanifold, in any case has k-dimensional measure 0. So you see that's extremely nice because it says that actually you can decompose the whole. This is really a very important fact that unfortunately is neglected. The preimage can be written, of course, as f to the minus 1y. For every y, you can always write the preimage as the part intersecting C union with the part complement C. This bit is a CQ submanifold, k-dimensional CQ submanifold, and this bit is a closed set of HK measure 0. So you can always decompose. Of course, this could be empty, keep in mind, but if it's not empty, then it is a CQ submanifold. So I should say, or empty set, one of the two. So this says that you can always decompose every one of these slices into a closed bit which has got k-dimensional Hausdorff measure 0, plus a bit which is a k-dimensional CQ submanifold. Very important fact. So we'll take a break there for a few minutes. Ah, yeah. Oh, sorry. Let me grab that.
V is open in RM or RK?
V is open in RM. It's the in RK. It's the xi coordinates downstairs. See it down there on that horizontal axis on the left of the board? V is in RK.
V is open in RK.
Yeah, and then you take the graph which sits up. The graph of U is the set of points xi, U xi. That's in M plus K. Right? Oh, did I write the... No, that's right, K-dimensional, yeah. Yeah.
Change the name of your axis.
Oh, yeah, I may have flipped my axes names, did I? Did I flip the axes? That should be Z down there. Yeah, let's see. I want the graph to be K-dimensional. So xi in RK cross RM. No.
No?
That's right, xi is K-dimensional. That's right, no, that's correct. And so the graph is Z equals U xi. Yeah, that's correct. I didn't flip the name of the axes. So that so here we are. So V is this set. And up here, so if you take a point xi down here, and up here you have Z equals, so the point up here is xi U xi. In other words, this is Z equals U xi. The graph, right? With me? So indeed, if you're mapping into, of course, you expect that, don't you? If you've got a rank M map mapping into RM, rank M map, then the pre-images should be K-dimensional, right? Which is the complementary dimension. The whole thing, this is Rn here. So N, this is in RK, this is in RM. Yep. Yep. Right. Yeah. Yeah. Into RK, but you see the graph. Yeah. U is in RK. Oh, right. U is in RK. Z. Oh, sorry. This should be. I've got something wrong there. Let's see. U is the map into RM, right? Yeah, I think that should be M. Is that correct? I think that's right. Is that does that look right now? Think up. Yeah, so U is. Yeah, this is in RM, so Z equals U xi. It's got M components, right? P in RK. Yeah, yeah, that's right. Yeah, that's right. When M is equal to 1, U would be real value. That's correct. That's the usual result. That's right. So, yeah, so I'll fix that up when we start again. Thanks. Thank you. No, I don't think so. Maybe, yeah, we can. Yeah, we can get rid of those now. Yeah, that's right. Yeah, thanks. Yeah.
Yeah, in fact, the original height I was trying to go.
Typo here. That U, the correct dimensions here, U is mapping into our M, and it's got M components. So the picture is as I've drawn it here. This Xi variable is in our K, and the Z variable is in our M. Like so. And then you get this nice picture. So we get this very nice. And you can actually say something else that's very nice about this. See this CQ submanifold? We could call this gamma, let's say, gamma of Y. K-dimensional CQ submanifold. Notice that by construction, the closure of gamma is contained, the closure of gamma minus itself. So one additional note here. If you let gamma y be this manifold part, f to the minus 1 y minus c, has the property that gamma y bar minus gamma y, you can sort of think of that as the boundary of the manifold, right? You can sort of, you could call that the boundary of the manifold. It's the closure minus the manifold itself. That's contained in this guy, which is contained in f to the minus 1y intersects c. So in other words, hk needn't be equal, it's contained. But hk gamma y is equal to 0, hk of the boundary. So a very nice picture. You can do this for any CQ map, any C1 map you can do this for. Or CQ in general. You'll get a Q-dimensional manifold if you have a CQ map. And notice it also works when, yeah, we can get rid of this now. This is no longer relevant. Notice it also works if M. Instead of Rn, you can have a submanifold of Rn plus L into Rm. Same argument applies that we used in the Euclidean case, exactly the same argument. Define the critical set in exactly the same way. The critical sets where the induced linear map has rank less than M, less than the maximum. Same argument. Shows that, again, f to the minus 1y equals f to the minus 1y intersects C. Well, of course, this is a tautology. This is always true, but the point is that this, again, is HK measure 0 for ln almost every y. Notice I do want to emphasize this is only for ln almost every y, because that's what the co-area formula told us, for ln almost every y in Rm. And this bit is a k-dimensional CQ submanifold. Or empty. Those two possibilities. And again, if we let this again be gamma y in the case when it's non-empty, again, HK of gamma y bar minus gamma y, that is equal to 0 because it's less than or equal to. This is contained in this bit, which has got measure 0, so it's equal to 0 for the same reason. The closure minus gamma y is contained in this, because the closure is just the points where you get to the rank less than M. So that's a very nice picture that works generally, even when you've got a mapping from a manifold into RMCQ map. Okay, so that's enough of that, and let's continue on now. All right, so by the way, this usually is referred to, these facts are usually referred to as the C1 Sard theorem. And let me just mention how it relates to the classical Sard theorem, since that's such an important theorem. The classical Sard theorem says actually more. It says that this is empty for almost every y. HK for HM, LM, almost every y in Rm. But there's a proviso, of course. There's always a proviso, provided F is at least of class, F and M are at least of class CK plus 1. So, for example, by the way, you'll see many papers and books and so on where they forget this fact and apply it to a C1 map, which of course is not true. For a C1 map, you've got to use this. For a CK plus 1 map, you can use the extra fact that it's even empty, which is better, which is even better than having measure 0. And for instance, if n is equal to 2 and m is equal to 1, then you're mapping a two-dimensional surface in some Euclidean space, RQ, let's say, R2 plus L. F is mapping into the real line, M equals 1. And this would be, now what does it require? Let's see, what's K in this case? K in this case is, K is always N minus M, so in this case it's 1. So the map would have to be C2 to use Sard's theorem. In higher dimensions it's got to be even better than C2, but in particular for a mapping from a two-dimensional submanifold into the real line, you need at least a C2 mapping to apply Sard's theorem for the classical Sard theorem. CK plus 1. It's 2 in this case. If you only have C1, then you have to use this. Okay, so that's enough of that. So that's the end of, that's as much as we need to discuss from chapter 2 of the text. So we're moving on to chapter 3 now. So chapter 3 is a chapter on rectifiable sets, countably rectifiable sets. Turns out to be an extremely important topic. So countably and rectifiable sets. So let me give the definition first. Definition. A subset M contained in Rn plus K. Such a subset is said to be countably N rectifiable. N rectifiable. If there exists Lipschitz maps, countably many Lipschitz maps. F1, F2, etc., where each Fj is a map from all of Rn into the surrounding space here, which is Rn plus K. Lipschitz maps such that the union of the images of these has to eat up almost all of M. So you look at the images of each of these. So you look at FJR in the image of the Jth map, take the union of all of those, and then you must have n-dimensional Hausdorff measure equals 0. In other words, M has to be contained in a set of measure 0 union with these Lipschitz maps. Notice it only has to be contained. There's no suggestion of equality. It's just got to be contained in such a union. That's the definition of countably and rectifiable. And so we want to study those and show that they're actually, in some sense, countably n-rectifiable sets, at least those which have locally finite Hausdorff measure anyway, n-dimensional Hausdorff measure. Such sets are in some sense, in some precise sense, which we'll make clear, like measure theoretic manifolds. I want to explain that as we go along. I'll get to that a bit later. In fact, later today. So anyway, that's the definition. It doesn't really say much, and it looks sort of like nothing. I mean, it looks sort of uninteresting, at least to me. Just contained in the countable union of Lipschitz images doesn't look very interesting, right? But I want to show you that there's actually a very interesting structure for these things. So the first lemma gives you a hint of that. That M is countably n-rectifiable. If and only if M is contained in union J equals 0 to infinity of Nj, where the 0th one of these has got measure 0, and each of the remainder, and each N1, N2, etc., is an n-dimensional C1 submanifold of Rn plus K. It's an if and only, it's equivalent. So that looks a little bit more, but still not terribly, doesn't really yet tell you what these things look like. We'll get to that in a minute, but at least this is a little bit more informative about what they look like. So we're saying that it's countably rectifiable if and only if it's contained in a set of measure 0 together with a countable union of C1 submanifolds. Notice this is not a disjoint union, it's just countable union. So it can still look pretty bad. Let's give the proof. Well, there's one trivial direction and one harder direction. The trivial direction is going this way. Proof in that's sort of trivial because you can use local coordinate representations for Nj. Each local coordinate representation for Nj is a C1 map, right? From Euclidean space, from an open set in Euclidean space into an open subset of the manifold, right? And so each local is C1, and hence Lipschitz on it, C1 on some open set, on some open V contained in Rn. That's what the local coordinate representations look like, and C1 maps, and hence Lipschitz. Remember, C1 maps are automatically Lipschitz on any convex subset. C1 maps are Lipschitz on any convex subset of the domain, right? So hence Lipschitz on any ball in V. That means that actually N is then covered by countably many Lipschitz images. So implies N is contained in countable union of Lipschitz images. Of course, you can cover any submanifold of Euclidean space by countably many local coordinate representations, so this is all countable. You can certainly arrange countable unions here. So, and that's it, and that means that you've got this. You can do that for each case. So there's nothing to prove there. That's the easy direction. Now the harder direction is the other way. So let's do that. So proof going in this direction. And this is where we get to use some of the machinery that we developed earlier on, a few lectures ago. Namely, I'm going to apply the C1 approximation theorem to each of these Lipschitz maps. So by the C1 approximation theorem, remember that was proved by using Rademacher's theorem together with the Whitney extension theorem. That was proof. And so by the C1 approximation theorem, there exists Gij, I equals 1, 2 for every j. There exists maps Gij, I equals 1, 2, etc. with Hn set of x in Rn such that Fjx is different than Gijx. And remember, the C1 approximation theorem says we can make this measure as small as we wish. So I can make it less than 1 over I, for example. So we can certainly do that. Hence, Hn of Fjrn, that's the image of the jth Lipschitz map, is almost all of that is contained in the union of the images here. So minus the union, I equals 1 to infinity, Gij Rn equals 0. So that's the first step of the proof. Just use the C1 approximation theorem to show that you can chew up almost all of the jth image, Fj of Rn. And then we've just got to show that we've now got to handle each of these images. Well, let Cij be the critical set of Gij. So let Cij be the set of x in Rn such that the Jacobian, notice that here we are in the setting where we're mapping into Rn plus k. So n is less than Rn plus k. So it's the area formula setting, if you like. And the Jacobian now means the usual thing that it means in the area formula, right? So J of Gij x is equal to 0. So this is the critical set of Gij, set of points where the rank is less than n. You can write it that way. It's the set of x in Rn such that the rank of the induced linear map Gij at x is less than n, less than maximum rank. So do that. Now, by the area formula, notice that the area formula implies that the n-dimensional Hausdorff measure of Cij, now this is not a 1-1 map, so the area formula will get that this is less than or equal to, because remember, the area formula is an exact equality counting the number of pre-image points. Here we're just taking one pre-image point for each point. So there's less than or equal to the integral over Cij of j Gij x dln x. So the area formula gives that. But notice this is 0 because on Cij, j Gij is equal to 0. So this is 0. So we get that Hn Cij is equal to 0. But then, of course, that implies that that the image of Cij also has n-dimensional measure 0. Implies that the n-dimensional measure of the image Gij of Cij is also 0 because that's less than or equal to the Lipschitz constant of Gij. Well, okay. At least on any compact subset, so I'd better be a bit careful here. For every compact K, HNGCIJK is less than or equal to the Lipschitz constant of Gij restricted to K times the Hn dimensional measure of Cij intersect K, which of course is 0. So for every compact K, you get that the image is 0, and of course K can be arbitrary, it can be an increasing sequence of balls, so that tells us that actually the n-dimensional measure of the actual image is 0. That's good. So these are sort of negligible then, these critical sets, as far as the image of them is concerned anyway. Okay, so, oh, I did this wrong, didn't I? This is wrong. Cij. This is supposed to be the image set, sorry. This is nonsense. Cij needn't have, I mean, one of the fj's could be 0, for example, then Cij is the entire space, right? So that couldn't be right. So this is, Hn Gij, Cij. Oh yes, I see. I didn't need to, oh, I'm sorry. I didn't need to say this. This is nonsense. This is what we want. So this is what the area formula tells us. The area formula tells us immediately that the image of the critical set has measure 0. Good. Okay, so that's that. So, okay, I think that we're back on track there. And so now that takes care of the images of the critical sets. Now what about the set of points where the rank is equal to n? So take x in Gij with rank equal to n, in other words, j Gij of x not equal to 0. Well, if you think back to our discussion of local graphical representations of submanifolds, you'll see that we considered this case, and it's very easy to prove in this case that there exists a row bigger than 0 such that Gij restricted to the open ball of radius rho centered at this point x, open ball, centered at this point x, is a C1 diffeomorphism it's a local coordinate representation, to be more precise. Local coordinate representation for the image set Gij B rho x 0. You remember this argument? It involved using the inverse function theorem. You compose this with a projection onto an n-dimensional space. Notice this is mapping up into Rn plus k. So you can compose this with an orthogonal projection onto an n-dimensional space and apply the inverse function theorem to that. Remember that argument? Well, that's what that showed, that we've actually got a local coordinate representation in that way. So that means, that is, that Gij of Rn minus, or any, well, we should again be careful about compactness. So on any finite ball, minus centered at, say, 0, minus Cij, you've got to leave out the critical set, that is equal to an n-dimensional C1 submanifold. Oh, sorry, not equal to, it's actually, yeah, let me say it this way. So we can do this in the neighborhood of each point of Rn minus C. So this is any point. So this is for every x in Rn minus Cij. You can do this. So that means simply that then we can take each of these then for each point x in that set. There's then this then gives you some radius rho, maybe small, where this is a C1 submanifold, n-dimensional C1 submanifold. So that means that the whole image is a countable union of C1 submanifolds. Gij of Rn minus Cij equals a countable union. union. Not necessarily disjoint, notice, because this map's not necessarily one-to-one in any sense. So it's a countable union of n-dimensional C1 submanifolds. Okay, and that's it then. That's the end of the proof. The rest maps to measure 0, has image 0. In the Euclidean space, this guy gives you the countable union of C1 submanifold. So we've shown that the entire entire union, you can do this for each J, for each of the images. So that means the entire union is contained in this entire union is contained in a countable union of C1 submanifolds together with a set of measure 0. So that's it. Okay, so that's so this turned out to be not very interesting. It's just a fairly. The only interesting step here was using the C1 approximation theorem. That's interesting, and that's the first time we've had to use that theorem. Okay, so that's our first characterization, but it still doesn't, as I said, tell us very much about what these sets really look like. So the next thing really does give you a much better indication of what these things really look like. And the next, this also, what we're about to discuss also will enable us to do analysis on rectifiable sets. At the moment, it seems sort of no possibility because then they don't appear to be anything like a manifold at this point. And you can do analysis on a manifold, but it's not clear you can do analysis on these things, much more general. Okay, so let's talk about that. So definition. So from now on, I'm going to assume a little bit more that M is going to be countably n-rectifiable, so you can think of that as either meaning this or this. This is actually what we'll mainly work with. This. So this is the, so that's, you should be thinking of that. And suppose M is countably n-rectifiable. In Rn plus K. And now we impose, from now on, we'll impose an extra couple of conditions. One is I want it to be Hn measurable always. We haven't been assuming that so far. So Hn measurable. And Hn M intersect, and it should also be locally finite measure. So Hn M intersect K finite for every compact K. Contained in Rn plus K. So we'll assume that from now on. And yes, okay, before I give the definition, I want to mention something else. So I don't think we mentioned this when we were talking about measures. So this is some convergence of measures. So you take a sequence, let's suppose it's mu1, mu2, etc. Any sequence of Borel regular measures. In, well, we're working in Euclidean space, but let's just take it. This also works in any metric space, or even more generally, actually, but let's stick to Euclidean space because that's what we're working in at the moment. So take a sequence and throw in one other one as well, just call it mu. So any sequence of Borel regular measures, then we say that mu j tends to, sorry. And I also want a finiteness condition analogous to that one up there. So these are with mu j k finite for every compact k. And mu also, first one, finite for every compact k. Then we say that mu j converges to mu in the measure theoretic sense. Mu j converges to mu means that the integral, you take any fixed continuous function with compact support. So here f is going to be a continuous real-valued function with compact support. So it's a C0 function with compact support on the Euclidean space, on RQ. And saying that mu j converges to mu means exactly that when you integrate fx with respect to mu j, that converges to the corresponding integral with respect to mu. And that should be true for every one of these f's, for every fixed f, which is C0 with compact support in RQ. So if you look in chapter 1 of the text, you'll find some discussion about this, including the fact that in a large class of spaces, if you start off with a sequence of measures which are uniformly bounded on every compact set, then you can always pick out a convergent subsequence, which it's a compactness theorem. You can always pick out a convergent subsequence which converges in this sense, right? By the way, it's maybe tempting for novices to measure theory to ask, is that the same as saying that mu j of A converges to mu of A for every Borel set A? And that's not true, because you have problems with boundaries of sets and so on. It's just easy to show that this is basically never true unless you have really trivial measures. But this is the definition of convergence of measures. So that's what we're going to use here. So let's go back to our discussion now. So here's the definition. Take a point x in M, or any point x in R K, typically in M, then has an approximate tangent space. Let's call it P, where this is an n-dimensional subspace of Rn plus K. We say that such a thing is an approximate tangent space for M at X, as an approximate tangent space at X, if the following is true, namely, you translate x to the origin and you blow up, for the moment let's take x in M, otherwise it's probably a bit confusing. It really doesn't have to be in M, but you should think of it as being in M. So let's for the moment take it in M. What we're going to do is translate x to the origin and then blow up by homothety, a factor lambda to the minus 1. So I'm going to use this mapping eta x lambda. That's going to be a translation and a homothety of Rn plus K. And namely, it's the homothety translation such that eta x k lambda of y is equal to lambda to the minus 1 times x minus y minus x. So it translates x to the origin and multiplies everything by the factor lambda to the -1. So it takes the little ball of radius lambda centered at x, and you apply eta x lambda to that. So this is the ball of radius lambda centered at x. It gives you the unit ball centered at the origin, radius 1. And lambda, you should think as lambda as being very small. So it enlarges things. Notice this is lambda to the -1. So when lambda is very small, it's a big homothety, expanding things out. And so M has got an approximate tangent space at x using this notation if the Hausdorff measure restricted to the enlargement and translation that you get by applying eta x lambda to M. So that's Hausdorff measure restricted to the, you take M, you translate it so that x goes to the origin, and you multiply it by homothety. So it takes a manifold maybe like that, with a point x here. So eta x lambda translates that so that x goes to the origin, and this gets blown up so that it almost looks like a line, because that was very curved, but then you enlarge it, so it's almost straightened it out to a line. So this is a typical picture, one-dimensional picture of what's happening. So if that tends to Hn restricted to P as lambda tends to 0. Now we've got to remember what that means. Here's our definition of convergence. This is a sequence of measures, so we've got to make clear what we mean there. That is, for every fixed continuous function with compact support in Rn plus k, the integral over eta x lambda of M, that's dhn. In other words, we're using this measure. That's the measure. We're integrating with respect to hn over that set. That's this measure of fx. Let's call it fy so I don't confuse you, because we're talking about x as being a particular point here. Dhy. That should converge to the integral of the same function over p. Dhny. So that's the definition of approximate tangent space. And you can see it happening here in this schematic. You're taking an enlargement here, and it's taking x to the origin, then you enlarge, and it takes you, and clearly it gives you the tangent line ultimately, right? It gives you these are parallel. It gives you the tangent line, right? That's so it's the n-dimensional analog of that. So that's the definition of approximate tangent space. Now, it's sort of a weak notion of tangent space, but it turns out that once we've got this, as long as we've got this kind of thing almost everywhere, then we can do some sort of analysis on the manifold, on the rectifiable set. Before we go on, let's make a couple of remarks. First of all, note that P, if it exists, is unique. Of course, that's obvious, isn't it? Because if you also were converging to some other P tilde, some other n-dimensional subspace, then you would deduce that the integral of any continuous function over P gives you the same answer as integrating the same continuous function over P tilde. Now, obviously, that means P must be equal to P tilde, right? Otherwise, you can clearly cook up a continuous function that vanishes everywhere on P, but which is positive on a set of positive measure on. So certainly, so this is clear. So P is unique if it exists, and that means we should give it a better notation. We should call it TXM. Now, let me tell you the main theorem now. that we'll prove next time. Here. So all these conditions, M countably unrectifiable. Oh, let's put the other conditions in first. So M, Hn measurable. Hn, M intersect K finite for every compact K. Yeah, assume that. Then there's an equivalence here. M is countably n-rectifiable. In other words, it satisfies that. If and only if M has an approximate tangent space almost everywhere. Hn almost everywhere, for Hn almost every x. Approximate tangent space T sub x M for Hn almost every x in M. That's the result. Very nice result. And that somehow gives you a much better idea about what countably rectifiable sets really look like. See, you've now got something you can do analysis with. You can take induced linear maps. We'll show later that you can differentiate Lipschitz functions, take directional derivatives, and so on. You can do various things on such a set using the approximate tangent space instead of the classical tangent space. So this turns out to be the key characterization of rectifiable sets. So I'll give the proof of this one next time. Since it's so important, I will give the proof. But for the time being, I just wanted to mention, what was that? That this is unique. Oh, yes. Another note here that's, that will put things in proper perspective is that a second note. If M is actually a smooth, if M is a C1, n-dimensional C1 submanifold, then of course Txm, the approximate tangent space, is exactly the same as the